this somewhere now. This is going to be equal to 10, 15 divided by 5 is equal to 3, right? So that's equal to 3. Okay, so then of course you also need the arithmetic mean of the explanatory variable. And I'm going to call this like that. Okay, so this is going to be the arithmetic mean here of that sample. This is also going to be 1 over 5 times 0 plus 3 plus 5 times 2 plus 0. This is going to be equal to 2. Right? Okay? Yeah, again, this is the explanatory variable, that's a dependent variable. Alright? So this is the explanatory variable, that's a dependent one. Okay? Now we also need the variance. Okay? So the variance of the dependent variable. Now the variance of the dependent variable here again, this is the mean of the squares minus the square of the mean. Okay, so this is going to be equal to, and then you have the mean of the squares. This is going to be equal to 1 over 5 times the sum of the squares of 3 squared plus 5 squared plus 2 squared plus 0 squared plus 5 squared. Okay, so this is the mean of the squares minus the square of the mean. So that's going to be the variance of the dependent variable. Okay, so now you have, okay, so 9 plus 25 equals 34, plus 4 equals 38, plus 25. Okay, so then you have 25 plus 38 equals 63. 63 divided by 5 equals 12.6. And 12.6 minus 9 equals 3.6. Okay, so this is what I got here for the variance. Okay, so this is the variance of the dependent variable. Okay. Now the variance of the explanatory variable, okay, so t minus 1. Similarly, mean of the squares minus the square of the mean. Okay, so this is going to be 1 over 5 times 0 squared plus 3 squared plus 5 squared plus 2 squared plus 0 squared. Okay, minus 2 squared, right? So this is the mean of the squares minus the square of the mean. So you have 9 plus 25 plus 4. Okay, which is equal to 38 over 5. Let me just do this again. So 9 plus 25 equals 34, plus 4 equals 38, divided by 5 equals 7.6, minus 4 equals 3.6 as well. So this is the same. Okay, so the variance is equal, if I'm not mistaken. Right? Let me just have a closer look. Plus 4 plus 25. Okay, divided by 5. I think it looks good. Alright, so in both cases the variances are the same. Okay? Process is stationary, right? But I mean this is just a sample variance. Okay, it makes sense, but this is just a coincidence, alright? So you have 9 plus 25 plus 4, okay, divided by 5 minus 4 equals 3.6. Yes, they're equal, okay? But this is just a coincidence, alright? So, and then I also calculate the covariance of the two, which is basically the autocovariance or the sample of the autocovariance, okay? Now here, I mean, of course, we use a little bit differently. Okay, so this is not the estimator, we use the sample values. Okay, so here for the regression analysis, what is the covariance? The covariance is going to be equal to the mean of the products minus the product of the mean. Okay, so here, if you use this in detail, so they have 3 times 0 plus 5 times 3 plus 2 times 5 plus 0 times 2 plus 5 times 0. This is the mean of the products, and then you take the product of the mean, so we have 3 times 2, okay? So dependent variable first, and then you have the explanatory variable. Okay, so you have 15 plus 10, okay, is equals 25. 25 divided by 5 equals 5. 5 minus 6 equals negative 1. So that's going to what I'm going to get here for the covariance. Okay? And then, of course, you have the slope, all right? So the estimator here for the slope. And this is not the intercept. This is the slope here, guys, okay? Be careful. This is A, right? So for the slope you have the ratio of the autocovariance, okay, divided by the variance of the explanatory variable, and the variance of the explanatory variable is this here. Okay, so this is the variance of the explanatory variable. Okay, so here, I mean, I'm talking about this guy here, 3.6, not the other one. I mean, of course, you could take the other one, but these are just here equal. I mean, this is just a coincidence. Usually you would not, so you have 1 minus 3.6, okay? So that's what it refers to, okay? So negative 1 divided by 3.6 is equal to, and this is what I have here, so negative 5 over 18, okay? And the intercept, okay, so that's the estimated for the intercept is going to be equal to the, maybe remember that, the mean of the dependent variable minus the slope times the mean of the explanatory variable. Okay, so the mean of the dependent variable, as I adjust the formula, okay, minus the slope, okay, or the estimate, let's say, times the mean of the explanatory variable. Okay, now here the mean of the dependent variable was equal to 3, okay, and then you have minus negative 5 over 18 times the mean of the explanatory variable. Okay, so what I get here is 3 plus 10 over 18, and 10 over 18, the result will be equal to 32 over 9. So that's basically what I would get here. Okay. All right. So that's the regression model that I would have been estimating here. Okay. Is this something that you understand, guys? Okay. Hopefully, right? So, I mean that is something that you're supposed to do. Okay. So basically, you would have that. Okay. So the estimator is as follows. Okay. So here you have yt, and then equals, and then you have 32 over 9, okay, minus 5 over 18 times yt minus 1 plus the residuals, okay? So this is the regression equation, okay? That's what you would get. Okay? We can basically continue also, okay? So I'm not gonna do this, but maybe you can do this just to verify that. Okay, so what you could do is basically maybe you can calculate the explanatory parts, okay, of that by just plugging in here the observed parts here in the regression analysis. So I'm not going to do this now. Okay, so this is going to be 32 over 9 minus 5 over 18 times yt. Okay, so these are, I mean, if you would calculate this, this is what you would get here. Okay, so you use data observations. Okay, so the first one would be 32 over 9. The second one will be, and you can do this on your own if you like. And after that, you could also calculate the residuals. Okay, I'm not going to do this. Okay, but maybe you can. So then you can see yourself that the sample means are equal. Okay, so the sample means of the total parts of y is going to be equal to this one. Okay, so basically you would have that the mean here would be also equal to 3. Okay, so the mean here of that sample is equal to 3. Now here, basically you would have the mean. Okay, the mean of the explained part is also equal to 3. So that's what you would get here. But I'm not going to do this. Okay, and then you would find out that basically that the mean of the residuals will be equal to 0. Okay, but again, this is not what we consider now. Just verifying the statement. Okay? And the same holds for the variance too, but we don't need to do this, okay? So because we can skip that by using the correlation coefficient. Okay, so let's calculate the correlation coefficient. Okay, so the correlation coefficient of the dependent variable and the explanatory variable, and this is going to be equal to the covariance of the dependent variable and the explanatory variable divided by the standard deviations. Okay, so the standard deviations of the dependent variable times the standard deviation of the explanatory variable. Now the covariance is equal to negative 1. Okay, and the standard deviations, I mean the variances were equal to 3.6. Okay, so basically you would have the square root of 3.6 times the square root of 3.6. Okay, that's what you would get. Okay, and that's of course equal to negative 1 over 3.6. Okay, so and that's just the same. Okay, so the correlation is going to be the same as the slope. Okay, but this is just a coincidence, right? So this is approximately negative 4.3, so it's relatively weak. Okay, and the coefficient determination will be just the square of this. Okay, so this is going to be the square of the correlation. Okay, so that's what you got. Okay, so 5 over 18 squared. Okay, so I mean, of course, the exact value is going to be 25 over 324. Okay, but if you have just approximate that, this is going to be equal to 0.0. Let's say make it to 0.077. Okay, that's the coefficient determination. What does it say? It says that approximately 7.7% of the variance of the dependent variable can be explained by the explanatory variable. That's relatively low. Okay, so here I mean, you could test this. Okay, but I would suspect that. Okay, so this process is not really a first order autoregressive process in general. Okay, because the explanatory power here is relatively low. You understand? Okay, so right, so this means that approximately, approximately 7.7% of the variance of the dependent variable can be explained. Okay. So this is the explanatory power of the regression. Okay. Again, this is not really high. Okay, but it is how it is. So that's how you would do it. Okay. Now you need to implement that, guys. Okay. So I just announced this before. This will be part of your second assignment. I will specifically send you it probably on a Sunday, I hope. Okay. So I hope I will make it until then. Okay, but that's going to be the second part. So you need to write a program that gives us the estimators of an autoregressive process. So the input argument would be a vector. Okay, maybe you're from an Excel sheet or whatever. Okay, and what you would do is you would basically you would I mean, this is what you would generate, you know, the autoregressive process as a result. Okay? Good. All right. Now we continue. Okay? Okay, so that's going to be just the first part, but you see this here. I mean, of course, you do this with your calculator in normal case. There are computers for that, but you'll see basically what is done. Okay, now the next chapter will be about testing, and we had some basic asymptotics, okay, that we were looking at. Okay, so what we have, okay, is, I mean, suppose that you have a I mean, in general case, suppose if you have an autoregressive process of order P, okay, so Y is an autoregressive process of order P. So basically what you would have is that Yt equals a constant plus A1 times Yt minus 1 plus A2 times Yt minus 2 plus etc. And then the last one is going to be AP times Yt minus P, okay? And then plus epsilon T, okay? All right, now basically here for all coefficients, I mean, let's say suppose that Y is stationary, okay, so if Y is stationary, then the asymptotics are as follows, okay? So then the asymptotics are, I mean, here you have the estimator, okay? So this is the estimator, okay, minus the true value, and I'm taking, you know, a certain value here. I mean, the ith coefficient, let's say. So the estimator of the ith coefficient minus the true value divided by the standard error. Okay, so this is the standard error of the coefficient AI. All right. So this is asymptotically normal. Okay, so that converges in distribution to the standard normal distribution. Okay. So as basically, I mean, if you have, let's say, or the number of observations converges to infinity. Okay. So this is asymptotically normal. Okay, and that is always true for any of the coefficients. Okay, so that we're interested in, so 1 to b. Okay, so you can use basically normal distribution for that. Okay, and this is always true no matter what kind of distribution you have for the standard or for the error term. Okay, so if you have this is the Gaussian error. Okay, then the coefficients will be following the t distribution. Remember that? So if this is a Gaussian step, I mean this is a Gaussian white noise, okay, so normal distributed white noise, then this will follow the t distribution, okay? But in any other case, basically you would have that is always true no matter what, okay? So I mean that's what you would get, okay? So you don't need to consider this, okay? Right, so basically, I mean, from a certain point, you just, if you have, let's say, more than 30 observations, then you could use the second order distribution. It doesn't matter. Okay? But this is always true no matter what kind of distribution the noise has. Okay? So this is independently true from the noise. Okay? And now, guys, this is also called the test statistic. So I will define this. This is going to be the test statistic, and this is Ti. Okay? So this is the test statistic. Okay, and if basically, and let's say you have the Null hypothesis, okay, so based on the hypothesis testing, okay, so here let's say the Null hypothesis is that the coefficient, let's say, the ith coefficient is equal to a certain value, let's say, it's going to be equal to A, alright, so let's say this is equal to the certain value, whereas the alternative hypothesis is that the coefficient is not equal to that value, right? So then, based on this asymptotic that we generate here, okay, then we can say that, let's say, if the absolute value, okay, so if the absolute value of the test statistic, and, okay, if the absolute value of the test statistic is greater than the 1 minus f a half quantile of the standard distribution. Let me just explain this here. So where basically z 1 minus f a half is the 1 minus f a half quantile, okay, of the standard normal distribution, okay. This is the 1 minus f a half quantile, standard normal distribution. what does it mean? Basically, if you put that value into the distribution function of the standard normal distribution, and you get 1 minus alpha half as a result, okay? And Ti is of course the test statistic based on that hypothesis. So here you have, of course, the estimator, okay, minus the value that you use for testing, divided by the standard error of the coefficient. Okay, so here you have the standard error of the coefficient. Okay, so this is the standard error of the coefficient, AI. Then basically, okay, then you could use that. That means that, okay, so if that is, the absolute value is greater than that, then the Null hypothesis, okay, so then the Null hypothesis, okay, which was that the coefficient is equal to equal to A, all right, so certain value can be rejected with error probability that is not greater than alpha. Okay, so alpha, guys, I maybe remember this, denotes the error probability. Okay? And if the absolute value of the statistic is greater than the 1 minus alpha half quantile of the standard normal distribution, then the Null hypothesis can be rejected at an error probability of, let's say, alpha, or not greater than alpha. Okay? Alright? If you don't remember what the 1 minus alpha half quantile is, I mean, just an example, okay, so just for you to recall it, because you have seen this before. I mean, suppose that alpha is equal to 0.05, right? So if alpha is equal to 0.05, then 1 minus alpha half, guys, is equal to, obviously, 1 minus 0.05 half, okay? So 0.05 is equal to 5%, so half of 5% is equal to 2.5%, so 1 minus 2.5% is equal to 0.975, okay? So this is going to be 97.5%, okay? So 0.975, sorry, I use this notation, 0.975. And the 0.975 quantile of the standard normal distribution, we had this in the MATLAB class, right? Maybe remember, is 1.96. Okay? Alright? So basically, what does it mean? What would be the interpretation? Again, this is what you see here. This is the density function of the standard normal distribution. Here you have 1.96. Okay? Since this is the since this is the 0.975 quantile, the area of the density function from minus infinity to 1.96 is equal to 0.975. So this means that since the total area is equal to 1, that here the remaining area is going to be equal to 0.025. So this is going to be 2.5% because the rest will be 97.5%, sorry. Okay? So here on the other side you also have, okay, so this is going to be equal to, here you have negative 1.96. Alright? So, and the area here on the left is just as large as the area on the right, okay, which is also equal to 0.025, which is equal to 2.5%. Because the density function is symmetrical, right? So here in between, you're going to have 95%. Okay? So that's where it's coming from. Okay, so 95% of all observations of the standard normal distribution are between negative 1.96 and 1.96. Okay? So that's basically what it means. And if the test statistic is beyond that, okay, so either greater than 1.96 or less than negative 1.96, which means that the absolute value of the test statistic is greater than 1.96, then you can reject the Null hypothesis that the coefficient is equal to A, which is a certain value that you use for testing. Okay? So that's what you would do here. Okay? Alright? Now, of course, maybe you remember this, that the stationary condition, okay, so if the process is stationary, okay, then of course, and you have the first order autoregressive process, then the coefficient will be equal to 1. Okay, so that's how you would test basically the stationarity of first order autoregressive process. But the problem with that is that if the process is not stationary, then the test statistic does not follow the standard normal distribution. This is something that you're going to see in further chapters. Okay, so we're going to have some problems with that. Okay, so this is not that easy as it appears. Okay, but I hope you remember these things from your statistics class. Okay, so I just need to repeat this. Okay, and again, the test statistic in particular, okay, will be something that you need to implement. Okay, so I will ask you to implement. I will give you a detailed description about this. Okay, so if I give you an autoregressive process, then you should be able to calculate, let's say, using the corresponding estimator, and your submission will be the program itself. Okay, so the little program that you write, you can use for submission. Okay, now let's stop here and we continue next time. Okay, all right. See you.